Hello and welcome to another power system analysis class. In the previous class, we continued power consumption in devices. We solved some problems on reactive power, real power, apparent power, how we calculate the current and voltage in a system, and how we calculate, compute the angles, power factors, if a system has a lagging power factor or a leading power factor. Today we will continue with single phase power system notations, three-phase systems, delta and Y connections. What are the benefits of delta connections? What are the benefits of star or Y connections? We would solve some problems on delta and Y connections. And finally, we would start with per unit systems as well. So in a power system, the components are usually shown as one-line diagrams. We show the generators as circles. The transmission lines are as single lines. And the arrows are used to show the loads. And this is from the previous example. Our generation was 28.8 megavolt amp reactive. Real power production was 16 megawatts, 17.6 megawatts, and the load was 16 megawatts and 16 megavolt amp reactive. Therefore, the difference between these two are the power that it's wasted in the system and the reactive power that we have. Now, that's the reason we use reactive compensation. As mentioned in the previous class, because the transmission lines act like an inductor, we have lagging power factor on them. Therefore, in the load, we usually add a capacitor or capacitive bank as a leading power factor to compensate for the lagging power factor. The key idea of reactive compensation is to supply reactive power locally. In the previous example, this can be done by adding 16 megavolt amp reactive capacitor at the load. And the reason that we do is to compensate for this reactive power that we have in the load. Compensated circuit is identical to first example with just real power load. Now, why do we want to do a reactive compensation? In other words, a power factor correction in the system? Because first, reactive compensation decreases the line flow. In this example, it decreased it from 564 amps to 400 amps. Now, reducing the current has multiple advantages. First, the line loss would decrease, and it's going to decrease at a rate of I square R, which is huge. And this is the main reason we use transformers in the first place. We want to increase the voltage at the generator, and we want to increase current at the generation side, and we would do the opposite at the load side. So again, we have a step-up transformer at the generation side. We increase the voltage and we decrease the current. Why? Because the current has a higher effect compared to the voltage on the amount of loss we have. For amount of loss is I square R, but for voltage it's going to be V square over R. So there's a difference, huge difference between that. Now, lower current allows utility to use smaller wires or thinner wires, or alternatively supply more loads over the same wires. You may think one of the expensive parts of a grid. Maybe the transformers or the generators, they're expensive, but the lines itself they require a lot of material. Nowadays, they are built out of different alloys, aluminum, which are very, very expensive. They will get very expensive. So even reducing the thickness by 1/3 has huge advantages and reduces the cost significantly. Reducing the thickness of the cable reduces the pole, everything that you need, the structure, safety measures that we have to put around it, all of that would be reduced. And the other advantage is obviously voltage drop on the line is less because we have less loss in the system. Reactive compensation is used extensively by utilities for the reasons that were mentioned, because we want to reduce loss and we want to reduce the current required to transfer that power. We also use reactive compensation in the load side as well. So most AC motors that you have in AC appliances, the appliances that have a motor in your home, they usually have a reactive compensator on, which is a capacitor, usually on the motor, AC motor as well. Now, capacitors can be used to correct a load's power factor to an arbitrary value. This is an example, a power factor correction example 1. We assume we have a 100 kilovolt amp load with a power factor of 0.8 lagging and would like to correct the power factor to 0.95 lagging. S is equal to 80 plus J 60 kilovolt amp. So phi would be equal to cosine inverse of 0.8, which is our power factor. Again, phi is cosine inverse of the power factor, which gives us 36.9 degrees. Now, here our target is to reach the power factor of 0.95. We want our power factor, as mentioned, to be close to 1 as possible. Therefore, the desired phi, or angle between the current and voltage, would be cosine inverse of 0.95, which is 18.12 degrees. So we have to go from 36.9 degrees to 18.12 degrees. Now the new apparent power would be 80 plus J 60 minus Q of the compensated or corrected reactive power. And if we calculate that, it's going to be 60 minus Q C over 80, 10 of 18.2, which gives us the 26.3 kilovolt amp reactive. So the compensation reactive power, the compensated reactive power should be 33.7 kilovolt amp reactive. Now, in systems, we usually have in power grids, power systems, we usually have distribution system capacitors, which you can see an example here. They come in different shapes and sizes, by the way. And they have to be serviced more often, usually, than transformers. Some of them have cooling, like oil cooling and so on, so they need to be serviced. But usually they will look like this. And depending on how much reactive power we have, we would put capacitors to compensate for that. Now, the definition of reactive power, as you know, this is just a reminder. PT is V max cosine of omega t plus theta V, I max cosine of omega t plus theta I. And if we expand that, we get to P cosine of 2 omega t plus 2 theta I minus Q sine of 2 omega t plus 2 theta I. Therefore, PT would be P times 1 plus cosine of 2 omega t plus 2 theta I minus Q sine of 2 omega t plus 2 theta I. Now, In power systems, we usually use three-phase, and I'll explain why we use three-phase. And when we use the three-phase that we use, the three-phase systems that we use must be balanced. And a three-phase balanced system has three voltages with equal magnitude. VM is equal, but with an angle of shift of 120 degrees. So we would have three, and you're familiar with this. This is just for a reminder. We have three voltages with identical magnitudes, but with 120 degrees. So VM is equal, but we have 120 degrees phase shift. We have equal loads on each phase, so the load must be balanced as well. And we would have equal impedance on the lines connecting the generation to the loads, or generators to the loads. So in a balanced system, we have equal loads, and balancing them is very important. And the transmission line must be, the impedance on that must be equal as well. Both power systems are almost exclusively three-phase. Single phase is used primarily only in low voltage, low power settings, such as a residential and some commercial. Now, this is an example of a balanced three-phase with no neutral current. And you can see that in a three-phase balanced system, IN, or neutral, is going to be IA plus IB plus IC. And because we have the same voltage, same impedance, but different phases, 100-degree phase, if we add them, the total neutral current would be 0. And because this current passing the neutral is 0, we can eliminate the connection between two Y connections. So again, the neutral current in a balanced three-phase star is 0, and the apparent power is going to be 3 VAN star, or conjugate. So it's 3 times the voltage of each, the power of each phase. Now you may ask, why do we use three-phase instead of single phase? There are multiple advantages of a three-phase power system. They can transmit more power for the same amount of wire. So if we have 3 single phase and a three-phase, the three-phase can carry twice as much as the single phase. The torque produced by three-phase machine is constant, which is very important. Why? Because we only have the difference between each phase is 120 degrees. So going from a positive to negative is very smooth and continuous. Therefore, we have a constant torque. The three-phase systems and machines use less material for same power rating. Three-phase machines start more easily than single-phase machines. That's a great question, and I will explain. I actually have a question for that. It comes down to amount of current that they are drawing and an amount of torque. That's the reason they start easier than single-phase machines. Let me give you an example. It's like if I want to push a car, or if 3 persons want to push a car, which one starts smoother, easier? I have to put more power to it because I'm by my own. So it's going to take a little bit of effort. But the three-phase, because it has instant torque, very high torque, it's easier to start for a three-phase. Does that make sense? So starting from beginning, imagine you have a car. Do you like to have a single-phase motor on it or a three-phase? Obviously, a three-phase has more torque, so if you're going uphill, it's going to be much smoother. The single-phase is going to have a lot of effort, therefore it's going to draw a lot of current at the beginning. And when it draws a lot of current. If it's not designed for a certain current and the current shoots beyond that, it's going to burn out the coil, right? So it comes down to the current and the torque that we have. And it's even different between a delta and a Y connection as well. And I'll explain about that. It's a great question, by the way. Now, there are two ways to connect three-phase systems. We have the Y connection and the delta connection. Y connection voltage is VAN. By the way, AN means between or we call it V phase. And VAB between two phases is V line. So the voltage that we have between the phase and neutral, this is called the phase voltage. Sometimes we call it V phase. And the voltage between two different phases is called V line to line. And this is VAC line to line, and this is VAN. Okay. Now, which one do you think is higher, V phase or V line in a star connection? Yes. So let's go through the phase voltage and I will explain. V line is higher, but by how much we will calculate that. So a phase voltage is going to be the voltage magnitude with the degree of alpha. VBN is going to be the same with 120 degree shift, and VCN is going to be the same magnitude with another 120 degree shift. Now, if we want to draw them, this is how a Y connection line voltage looks like. The longer the vector is, meaning it has a higher magnitude. So you can see VAN, BN, CN, phase voltages. And between each phase, you have a 120 degree phase shift. And between the line voltages, also you have 120 degree phase shift. Now, let me erase this. When you want to find the voltage between two phases, when you add these two vectors, you get this. So you get this vector and this vector. And this is going to be VAB, which is VAB is equal to VAN minus VBN. And if I calculate that, in this case, alpha is 0. VAN minus VBN is equal to the magnitude of V, 1 minus alpha, minus 1 with the degree of alpha, minus 1 with the degree of alpha, plus 120 degrees. Therefore, when we calculate that, we're going to get square root of 3 magnitude of V with the degree of alpha plus 30 degrees. And it's going to be the same for VBC, but just with 120 degrees shift compared to VAC. So it gives the same magnitude, but with negative 90, and the other one, again, another 120 degree, which is going to be plus 150. So this is VAB, VBC, and VC. So you can see that the line to line voltage, the magnitude is square root times VAN. So VAC is square root of 3 VAN. So V line is square root of 3 times V of the phase. Now, to define the voltage current across device to be a phase voltage or current, we define the voltage current across or through lines to be the line voltage current. Now, V line, as mentioned, it's going to be square root of 3 times V phase with a degree of 30 degrees. But in a star connection, I line is equal to I phase. And the parent power of 3 phase is 3 times V phase I conjugate of phase. So as you can see here, this is I line. It is also I phase. So in a star connection, the line and the phase current are the same because they are in, both these phases are in series. So I of the phase, or IAN, is equal to I of the line, or IAC, for example. Now, another type of connection, three-phase connection, you're already familiar with this as well. It's called the delta, three-phase delta connection. And again, here, the magnitude of the voltage and current are equal for the three phases. It's balanced. But the relation between the phase voltage and phase and line voltage and phase current and line current is the opposite of a star or Y connection. Here, V, I'm going to just mention it with V phase, is equal to V line, but I line is square root of 3. I'm sorry, I phase is 3 right square root of 3 I line. Now you can see here the relation between the phase and the current. So if we have a current coming in, it's going to be divided by 2. So therefore, IA, or I phase, I'm going to write it, it's going to be square root of 3. So I line. It's going to be square root of 3 I phase. In other words, IA is going to be square root of 3 I of AB. Obviously, with the degree of negative 30 degree, and we're going to have 120 degree shift for all of them. So in the previous one, we had this graph for voltage. Now we have it for current. And again, you can see 120 degrees shift in the phase current and 120 degrees shift in the line currents. So in a delta, V line to line is equal to V phase. Now, some motors are designed for both star and delta connections, but other motors, not all three phase motors, are designed for delta and Y connections. Only some motors work both on delta and Y connections. And the first question that we have here for this quiz, I'm going to do a small quiz, is which one is better? Is delta connection better for a motor or Y? And usually, which connection do a motor start with? So this is the first question. By the way, this is the results of your previous exam as well. Josh, not here. Jones, yes. Alia is not here. Taylor, did you take the quiz last time? No, you two didn't. Okay. So the first question that we're going to have is that a three-phase induction motor can be started using a star delta starter. Which connection is used at startup, star or delta, and why? I want you to explain it in terms of starting current and starting torque. I'll give you 5 minutes to think on this. Again, for a delta connection, V phase is equal to V of line, but I line is square root of 3 of the phase current. And for the Y or star connection, I line is equal to I phase, but V line is equal to square root of 3 V phase. Did you write down or you need more time? Okay, I'll give you a few minutes. Just 1 minute, I think. Okay. So before I start with the answer, I just wanted to show you this. This is a plot on a three-phase motor. This is what you would usually see in a three-phase motor that has delta and Y connection. And you can see on the left, it says delta and the voltage that it operates on delta connection, and also the star or Y connection, and also the wiring. The three-phase motors that are capable of running both in star and delta have 6 terminals instead of 3. And the way that we connect them, we connect U1 to W2 and so on. And for a star connection, we connect U2 to W2 to V2, and the 3 others will be connected to the phase. Now, depending on the order that we connect them to phase, it's going to be a clockwise or left turn, what they call left turn, right turn motor. So by just switching these 2 phases, for example, you can determine the direction. So if you have an elevator, you want to go up and down, you would just change these. Now, the answer to this question is we start 3-phase motors on Y connection. And the reason is when it's an Y connection or star connection, each phase receives VL over square root of 3, which reduces the line current to about 1 over square root of 3 of the delta value, and starting torque to about 1/3 of the full torque. So Y connection has lower torque, delta connection has higher torque. Y connection has a current which is 1 over square root of 3 times less than delta connection. Therefore, you're going to have a lower current. And when we start with a lower torque, and then we would move to a delta connection, which is a higher torque. The reason why we do that is most of the times we want to have a smooth start. So for example, if you're in an elevator, you just don't want to have yanking or cable. We don't want to put the cable on too much pressure. We start with Y, and then we move to delta. And this transmission is pretty seamless. It takes sometimes couple milliseconds, and we have a device that does that transition between Y and delta connection. Now, after the motor accelerates, it's switched to delta for normal operation at rated voltage, torque, and power. Now, second question, I want you to put your tablets and everything away for this one. Another question, we assume we have a delta connected load, which is supplied from a three-phase 13.8 kilovolts line-to-line source. Find the phase line current, power factor, and apparent power with the load of 100 with a degree of 20 degrees ohms. Again, I'll give you 5 minutes to solve this problem. Do you need more time? Are you done? Now, let's go. For this question, first we want to find the current, and the current is calculated using Ohm's law. We use the voltage divided by the impedance, which gives us a current of 138 with a degree of negative 20 degrees amps. And this is the line to line or line current, by the way, because we divided the line voltage over the impedance. And we can do the same thing for different lines, IBC and ICA. All of them would have the same magnitude. The only difference is 120 degrees shift in their phase. Now, to calculate the phase current, we can subtract two of the line currents. It could be any of two. Or in other words, we can use the equation square root of 3 times the line current. Yes. And then with a degree of negative, adding negative degrees to that. So negative 30 degrees to that. Now, if we calculate that, the current would be 239 with a degree of negative 50, negative 170, again 70 with 120 degrees shifts. The apparent current, the apparent voltage is going to be 3 times V line to line, I line to line conjugate. And when we calculate that, gives us 5.7 with a degree of 20 degrees. And if we convert that to the rectangular form, it gives us 5.37 plus J 1.95 megavolt amp. Now the power factor is going to be cosine of phi or cosine of 20 degrees, gives us 0.94 lagging. Okay, thank you. If I can please have your quiz back. Put your names on it. Did you put your names on it as well? Okay, thank you. I will grade them and return them to you on Wednesday. Now, for delta Y transformation, to simplify analysis of balanced three-phase systems, delta connected loads can be replaced by Y connected loads with ZY equal to third of Z delta. And delta connected sources can be replaced by Y connected sources with V phase equal to V line divided by square root of 3 with a degree of 30 degrees. So again, usually we want to replace delta loads with Y loads and delta sources with Y sources. We can do it as follows if we want to do that. Now, this shows a delta Y transformation, and the proof, again, from a delta side, we get IA is equal to VAB over Z delta minus VCA over Z delta, which would be equal to VAB minus VCA over Z delta. Hence, Z delta would be VAB minus VCA over IA. Now, from the Y side, we get VAB is going to be ZY, IA minus IB, and VCA ZY times IC minus IA. Therefore, VAB minus VCA gives us ZY times 2IA minus IB minus IC. Since the combination of all the currents gives us 0, it's a balanced system. Therefore, IA would be equal to negative IB minus IC. Hence, VAB minus VCA gives us 3ZYIA. So 3ZY is going to be equal to VAB minus VCA over IA, gives us Z delta. Therefore, ZY is equal to third of Z delta, same as mentioned in the previous slide. So Zy is third of Z delta. Now, this is an example of a three-phase transmission line. There is another line on top usually. That's not part of that. Usually that's for lighting and so on. So if you have a very thin wire, that's not part of that three-phase. Now, to make everything simpler and easier to calculate, we use a different type analysis. We call it per-phase analysis. So per-phase analysis converts, technically, it's modeling a three-phase like a single phase. So instead of showing all the three phases, you just show one line. And it's the principle behind this that we showed in the beginning of today's class. So this is a three-phase system, for example, but we only show it with one line. And this method is called the per-phase analysis. Per-phase analysis allows analysis of balanced three-phase systems with the same effort as for a single-phase system. Balanced three-phase theorem for a balanced three-phase system with all loads and sources are Y-connected. So we have to convert, if you have a delta connection, you have to convert it to Y connection. And no mutual inductance between phases, okay? In reality, we have mutual inductance between phases, but for per-phase analysis, we neglect that. It's very, very negligible. It's very small, by the way. Now, after we've established that, then all neutrals are at the same potential. All phases are completely decoupled. All system values are the same sequence as source. The sequence order we've been using, phase B lags phase A, phase C lags phase A, is known as a positive sequence. Later in the course, we will discuss negative and zero sequence as well. So per phase analysis, we do it for one phase, like a single phase system. It's a Y connection system, and we would assume that all neutrals have the same voltage, and also there's no mutual inductance between phases. And this is actually the beginning of the most important part of this class is per phase analysis, and we would do per phase analysis. And probably we have an OPAL-RT device. We would do some simulations as well. If we have time, I would probably design a little lab that you would do, software simulation using maybe Simulink. I don't know if you have MATLAB, but there are other softwares that we can use to do a per phase analysis. Okay, thank you so much. That's it for today. We finished this lecture. I will see you on Wednesday. If you have questions, by the way, in the meantime, just please let me know.